Hello everyone, let's continue then with the seminar. So the last class we finished, well, we did not finish 9, the exercise number 9, so let me finish with that. So we have 9F, right? And if anyone can solve this problem, some mathematician can solve it. So let me write that. If anyone can solve this problem, some mathematician can solve it. If any, here. Paul is a mathematician and can't solve the problem. Paul is a mathematician and cannot solve the problem. Therefore, the problem cannot be solved. Therefore, the problem can not be solved. Okay, first of all, I will ask you, everyone, to join our Zoom conference because I want to see you. Well, if you can, just turn on your camera, okay? And join, and please write some plus that you are here with me right now, okay? So, this is the last problem of this kind that we will have, and let's do it then. So, if anyone can solve this problem, so first of all, right, we have that we're talking about people, right, just like that, and the predicate is we can call it this way, can, and mathematician. Yeah, let's do it that way. And then we can write that if anyone can solve this problem, so if there exists somebody that can't solve this problem, right, then some mathematician can solve it. So from this we can conclude that some mathematician, let's write math, because mathematician is a long word. Then there exists a mathematician that can solve it. So there exists a mathematician and he can solve it, right? So this is the first statement here. Now, Paul is a mathematician and cannot solve the problem. So, and so this is, we have here this. So, and Paul is a mathematician. Paul is a mathematician, but he cannot solve the problem, right? Paul is a mathematician, but he cannot solve the problem. Therefore, from all this, we conclude that therefore the problem cannot be solved. So that nobody can't solve the problem. That's our conclusion. Okay. So, first of all, this is true or false. How are we going to see this? Any ideas? So again, let's read this. If anyone can solve this problem, some mathematician can solve it. Paul is a mathematician and cannot solve the problem. Therefore, the problem cannot be solved. What can you tell me just from these words? Why?
Because exists one people who is not mathematician can solve.
Yeah, so Paul cannot solve the problem, right? But it doesn't mean that there exist more mathematicians who can solve it, right? So this is not true. That nobody can solve it. Okay. So let's show this. So this is false. So let's assume that. So let's say that that this is false, right? So it means that there exists. So nobody can solve it. So there exists somebody that can solve it, right? If there exists somebody that can solve it, then there exists a mathematician that can solve it, and then there exists a mathematician that can solve it, right? So this is true, and this is true. So this will be, so these all have to be true, right? And this is true. And this has to be true, then this has to be 1, right? This has to be true. So then we have that if there exists somebody that can solve it, then there exists a mathematician that can solve it. And we need this to be true. So this has to be true, and this has to be true. And then if Paul is a mathematician and he can solve it, yeah, it's true. But so we obtain that when we assume that this is false, we obtain some values here, and everything holds. Then, since we have one here true and here false, then everything is false, right? So, yes. So, huh? This one, because this is true from here. Yeah. Then this has to be true. And and this has to be true, and everything works, okay? So we assume that this is false, and we obtain that for this false statement here, this is true. And then we obtain true and false, so the implication from true to false, then this is false.
Don't have problem. I just can't understand why this is.
What this is true?
Yes. We can obtain the same result if we assume that it's false. Can or not?
No, because if we assume that this is false, then this is going to be false, right? Because we obtain one. Yeah. So yeah, I mean, there's no. We don't need to do all this actually. We just from here, from the very sentence, we can find the solution. Actually, if we start to do this, we can get confused, I think. So sometimes it's quite obvious everything. Okay, and.
Why does exist
Here? X. If anyone if there exists, no?
If anyone is not,
If anyone,
Yes.
if everyone, yeah, for all?
if everyone can learn some mathematician.
Ah, yes, sure.
If somebody can, it's not all that.
Yeah, yeah, you are right. Yes, if anyone can solve it, so for all can solve it, then this is true. Yeah, okay, yeah, thank you. So everything holds anyway, because if there exists, then we can assume all this, okay? So we finish with this, finally. That's very good. Now let's move to strings, and I'm not sure what you studied before, so yesterday in the last week, but let's recall in general what the strings are. Okay, so first of all, what is a string? Yeah, which items? Yeah, so we have an alphabet, A, right? And we have some items here, some letters or something, some elements, symbols, let's call it symbols, right? So this is an alphabet. And we have some, I don't know, X, maybe some symbols of A. Okay, X, I mean X, anything can be a symbol. So this alphabet can be the letters in English or any language. This can be the natural numbers, the real numbers, or anything you want. Okay, and now we say that a string, let me just define it the same way your lecturer did. Okay, so let's call S will be some string over A. Okay, so some S will be some string over A. Now let's call SA the set. So this is going to be the set of all strings over A. Okay, and let's define this. Say that this belongs to SA. So, and this is called is the empty string, right? This is the empty string, and the empty string belong to, so the empty string is a string in any alphabet. Okay. Now we define some rules. So we are not going to define what a string is, what an alphabet is, but I'm going to tell you how you can construct them, how you can obtain all the strings you need. Okay. So this is called the recursive definition. Okay, and so let's take some rules. So everything I'm telling you, it's from your lecture, but it's quite important. So the first rule is that is this one. Yeah, that the empty string is a string over any set A, any alphabet A. And the second is that for all X in A and for all S in SA. So for any symbol of your alphabet and for any string of your alphabet over your alphabet. Sorry. X column S is also a string. Okay? So we have the empty string, and now if we have some symbol in your alphabet and you have any string, you can obtain a new string in this way. And finally, all strings in A can be obtained used by 1 and 2. So no matter what the string we have in our alphabet, we can construct it, we can obtain it this way. Okay? So give me some example of a string. I don't know, over the natural numbers, for example. Some example. Yeah. So 1, 2, I don't know. Anything of that kind will be a string. Okay. And we say that. So if we have this n, by definition this will be equal to x1 column x2 column x3 and so on xn. Okay. And of course the empty string. Here you need to add this and this, I don't know, yeah, but you don't need to do this always. I don't know, the lecturer just sometimes he does it, sometimes he doesn't, so I don't know. I think you don't need to, but okay. But in the formal way, you have to put all this here, okay? What else? Yeah, and we have a couple of axioms. So the number one is the following, that for any symbol of A and for any string of A, this is not true. So we cannot represent the empty set. We cannot represent the empty set in this way. So we cannot construct the empty set if we add, right, some symbol from A to some existing S string. Okay, this is the first one. And the second one is that for all X, for all Y, and for all S, for all T, X column S will be equal to Y column T if and only if X is equal to Y and S is equal to T. Okay, so we have that any strings are equal if and only if. So this is called the head, right? And this is the tail, right? Two strings are equal if and only if their heads and their tails are the same. Okay. No, the length can be any. I mean, no. Look, we'll talk about a bit later. Okay, about length. Okay. And by now I think that's all we need, right? Let me check the first. Yeah, that's all we need by now. So exercise number 10.
or just the x added to the next thing?
Sorry, what again?
Symbol between x and the in the second axiom.
Yeah. What's the problem?
There, do you have symbol?
Ah, yeah. Sorry. T.
And also next, I'm asking you if there is a symbol between x and the s.
Look, we have X, Y, N, S, and T. Yeah.
There is a symbol between them.
A symbol here? No.
What is in the bracket?
That this is equal to this.
Yes, but you have got x.
Column X, column X, column S, Y, column T.
Yes.
Okay.
It's not so visible.
Ah, okay. Sorry. Yes. Okay, so let's resolve problems with this. Everything will be a little more clear. Okay. So number 10 is prove formally that 1, 2, 3 is not equal to 1, 3, 4. So 10, 1, 2, 3 is not equal to what? 1, 3, 4. So what do we need to do to prove this? So we have to show that these two elements, that these two strings are different. So let's suppose that they are equal, right? And we will get some contradiction maybe. So let's suppose that 1, 2, 3 is equal to 1, 2, 3 to 1, 3, 4. Okay, what next?
You can think the first one is 1, comma.
Yeah, so this is equal to what? This is equal to 1 column 1 2 3, right? And this is equal to 1 column 3 and 4.
And then we do this again.
Yes, here there is no contradiction as you.
Okay, yeah, we can do this again, but what do we need to do first?
There is the second axiom.
Yes, we have this axiom, and then we say that these are equal if and only if this is equal to this and this is equal to this. Then 2, 3 should be equal to 3, 4. Right? Now, what do we need to do here? Yes, the same thing. So, and we have to do this many times. So 3 equal 3 4. And so this is equal if and only if 2 equal 3 and 3 is equal 4. But 2 is not equal 3, right? So we have contradiction. Then this is not true. Then this is true, okay? And it's proof, right? So look, yeah, this seems very easy, very, I don't know, like dumb or something, but you have to see that even to prove these simple things or very complicated things, all we need to use is this, no more. Okay, all we need to use is this. Sometimes it's not very clear when do we need to use or where do we need to use it, but you will see. Okay, and this is number 10. Okay, now this. Okay, this. No, this one. Where is this thing? So this was A. Well, exercise B, I think is quite clear. So let's just do exercise number 11. Okay. So, prove that the length of a student is equal 7. So we have an alphabet A. This is English, let's call it. So this is the letters in the English language, okay? And then we can construct the following string, student. Yes. And now we need to prove that, okay. So, first of all, functions. So we can, from now on, we can define some functions. Let's define the function length, okay? And again, I'm not going to tell you what exactly this is. I'm going to tell you how you can find it, okay? Then, we have two rules for this. So two rules to construct this function, and they are what? Did you see this on your lecture? Yes. So tell me. Yeah. So how can you define the function length?
Number of elements in the set.
No, actually no, because what you're saying, yeah, it's correct, but it's not. Look, everything we are studying right now, it's very, very, very basic. So, like as your lecturers say every time, we have to teach a computer to do things because the computer doesn't know how to work. So, if we say that the length is the number of elements in this set, we actually don't know what a set is right now. The computer is not going to understand anything. So if you say that in your exam that the length is the number of elements, is not correct, okay? Because you have to think how the computer is going to understand everything, okay? Yeah, but before that, so what is the length of 0? And then what would be the length of S of X column S? Yes. And that's it. Okay. This is all we need. No more. Okay. Now, knowing this, we can find this. So we have to prove that the length of student is 7. So let's find the length of a student. So the length of, and what else? What else do we need to write here? No, it's okay. So the length of a student will be equal, so length of student again. Yeah, I know. But of S, what do you mean S? So what is a student? A student is actually this. Yes, student, right? What is, but we don't know what is the length of S.
We will get this by the program.
Yeah, so 1. These are different things. If you say the length of S, we don't know what is the length of S. We know that S is a symbol of A. Then, since this is just a symbol, we can write.
If you write it by what I'm telling you, by the property, we can get the length of S.
So you are telling me that we can write this? The length of S plus the length.
I'm not telling you that. I'm telling you that it's equal to length of S column.
Okay, yeah, that's true. Okay, yes. So let's write it right here. So we have 1 plus the length of what? Student, right? This is equal to? Yeah, 1 plus 1 plus the length of udent, and so on, right? So we obtain 1 plus 1 plus 1 plus 1. So 1, 2, 3, 4, 5, 6, 7, plus the length of empty set, of empty string. So this is 0, right? So this is equal to 7. And that's it, okay? So formally you need to write this 7 times. But we're not going to do it, of course. Okay? That's it. Very, very simple. Next. Okay, number 12. No, number 12. Prove formally that. Okay, so we saw this function length, right? Now, what about this function append, right? Append. So how do we define this function? So did you study this? Yes? No. It has to be something like this.
Column S is equal to
for x and empty is equal x
To of S and
is column
this is S, okay? This is the first one, and the second case we need
append of S and
empty set what? Twice?
x column s
No, we don't need that. This is something we can prove that is true from here, but we are working with the basic properties, okay? So the basic property is this one. Okay, actually, is this one or
Yes, no,
is this one, right? Okay, and the second property,
append of X and
append of what? So, yeah.
X and
Yes.
equal to X column append of S and
Append. Yeah. This. Well, it looks like it's true. So let me find. Where is that? Okay. Or no, it's not that way. Yeah, you know that. So this is equal to x column up st, okay? Yeah. Now it's correct. And this is, by the way, otherwise. This way. Yeah. So this is the basic one, and using this we can prove in this order, right? So int s empty set. But this is the basic one, and this is the second property. That's it. So for all x, s and t, for all s and for all t, this holds. So what's, for example, the app of, I don't know, 2, 3, and 3, 1? This should be just 2, 3, 3, 1. Okay? Do you see why? Yeah. So you tell me, yeah, okay. Yes, that's it. Now, exercise number 12. Prove formally that, okay, we have to prove this formally. Okay, prove formally, prove that what? 1, 2, 3. 1, 3, 2. One, two, three, two, 3, 2. So we have to prove this. You want to do it? No? Okay, do we have any question from here? I can... okay. So the second, right?
No, not for that, but for 1, 3, 2. We need to say that 1, 3, 2 is equal to 1 column.
Uh-huh. Yeah, well, yes, but we know that from the definition. So every time we write this, it will be clear that we are talking about this. Okay. Then we need to use this one. Then we write 1. So equal to what? So 1 column F of what? 3, 2 and 3, 2. Okay. Yes. And then
We do the same for
yes, we have to do exactly the same until we get the following. Until we get, so 1, we have 2, and then 3, and then we'll have 2 column up of what? Empty string, and 3, 2. And this is 3, 2 because of this, right? So we have that this is 1, 3, 2, and 3, 2. So this is equal to 1, 3, 2, 3, 2. Okay. And that's it with this one. Is everything clear? Yes? There is everything clear? I guess so. Could you repeat the first action, please? Which one, Ali? You mean this one or which one? I don't know. Yes, okay. So next. Here. Let's press this. Number 13. We have to define a new function in it that removes the rightmost symbol from a string. So we need to define this function. Such that we obtain and the function on 1, 2, 3 give us 1, 2. So we need to define this function formally such that we take out the last symbol on the right side. Yes? In this case, we take out the right symbol and we can, yeah. See. This is something we need to define. This is a function, a new function like length or append. Now we define this new function, but this function is just taking out the last symbol we have here. Okay, so now you see 1, 2, 3, 1, 2. Solution. Okay, how are we going to do that? So look, we need to create some rules that looks like this one, but for this function. What do we need to do? So we need to put some, to create some rules. So tell me tell me. I listen to your ideas. So what's the first one? The obvious one. Yeah, that's what our function does.
We can try to get limits of empty and S.
Of empty. So how many, look in this case, how many strings do I have here? 2 strings, right? How many strings do I have here? 1. Yeah, 1 string, okay? So this function takes 2, it's defined over in 2 values, 2 variables, okay? 2 strings, and this one just for 1 string, okay? Then we have to, okay, so the first thing we have to do is this. What happened when we define this function over the empty string? What do we obtain? Empty string, right? So this is the first rule, right? Like we are doing here. What if we add to some string the empty string? And the same way, well, already in the length of an empty string is 0. So always we start with an empty string. And we say that the value of this function over the empty string is the empty string itself. Now, what else?
We can try to make the image of empty and S.
What do you mean? No, we have to just do it for this
We can
one.
try to make image of one element and empty.
One element. So one element x. What do you mean end? Column, right?
No, it's equal to this. According to the single property of the definition.
So is what?
Sorry, but can you tell us exactly what this init does? If we have one.
We take this element out.
Yes, the last element of the last element input anything, whatever the length.
Yeah.
So
It will be any.
the output is X
Here x. Why?
because in beneath the last element.
This is an empty.
Because the last element of any string is the empty string.
Then it will not delete any element.
So here he will
Yeah.
get empty.
Yeah. Look. So. What if we add to some string the empty? No, yeah, it's not the way I said it. No, if we have some string and we add this empty, then we have to delete this one. So we obtain x. Because in x is already, the empty string is already here. So we are adding some empty string to some existing string. Okay? No, wait. No. No, wait. So if we have
Is maybe like add when x column string and x out of the function.
you mean that we can do this? Well, I don't know if we can do that. We don't know, so that's what we have to find. Okay, let me think 1 second.
X is a simple string or X is a simple string?
Okay, let's define the following. It's much. This is S. We have a string here, non-empty string. So yeah, any string here. So what is this equals to? Just x.
No, x and x column x no and minus no without the
We don't know what minus is.
without the last element of s.
Yeah, so how do we write that? How do we write that? We need here s without the last element. So it's our function itself, right? So yes, so it's x and s, but without the last element. Now, if we see at this, what can we say about this one? 1 second. So if we sorry. Yes. Of course, this is empty. I was confused. X is not a string. Yeah, so for all x that belongs to the alphabet, and this is for all x belongs to A, and for all s that belongs to SA. So this is just a string with one element, okay? So we just put it out and we obtained empty. Yeah, I was confused. This is a string, and that's it. Okay, so this is the solution. So in this way, we can find this function in it for any string we want. Okay, and that's what we were asking for. That's it. So. So number. So this was number 13. Oh, yes. So number 14. 14. Let's do it here. Prove that formally that so we have that for all s and for all t, for all the strings over the alphabet A, if the app of s t is equal to the empty string, and then this is if and leave, right? It's written. Yes, if only if S is the empty string and T is the empty string. Yes, if and only if. So this is true if this is true. How do we prove this? Any ideas?
So we suppose both of them are false.
We what?
Let's suppose that both they are false.
And then what? So let's suppose that
Let's suppose that this, like, it's equivalent.
yeah.
So let's suppose that the left element is false and the right element is false.
false and false? No, we have to suppose that something. If we have false and false, then we obtain that this is true. You see it? So what? The best idea here is to look. We say that this is true if this and this are empty strings. So let's look what happened if S is an empty string. So what happened if S is an empty string and we know that this is true? What value do we obtain for T? So T should be an empty string as well. Right? So if we say that if we put empty string S here and we obtain that T is not empty, then this is not true, right? And then what happens if we say that S is not an empty string? What T should we obtain here?
We must
So let's take just two cases. Case 1 and case 2. In this case, we say, let's say that S is an empty string. Yes. And in this one, let's say that S is not an empty string. Yeah. In this case, what value of T should we obtain? Empty. And in this case, non-empty, because if we have that S is non-empty and T is empty, then this is not true, right? Because of end here. So we take some values, we put it here, and we get some values for T. And that's the way we have to do it, okay? Okay, let's do it, you will see. So case number 1, S is an empty string. Then we put this value here. Right? This is equal, and this should be empty, right? So what does it mean? No. So what do we need to look at? So look, we have this and we don't have it. Okay. So we know that the app of S empty string is empty by definition, right? And we have that the app of some string and T is empty. So this is true in what case? Yeah, even so, if and only if T is empty string as well. Okay, so for S empty string, we obtain that T is empty string. Huh? Opposite. Okay. This is. Let me check. What did I write here before? I just forgot because. Let me check. Where is that? Empty and S, yes. Then we have to prove this. Okay, yeah, we have to prove this. Did you prove this?
It was.
Okay, so let's prove it. Because to show this, we need to be sure about this. Okay, so let's prove that this is true. So let's write the following way. So we have to prove this. How are we going to prove this? What? No. So we know that we know this by definition, yes? But this doesn't mean that this is true, right? There are different things. So what can we do? So we have a fixed value here, the empty string, a fixed string, and we have some s. So what values can s take? So let's do it by induction, right? So do you remember about induction? I think you had that. So let's take some property. We'll say that this property is this one. And we need to show this for which s? For s empty string and for s some string or some other string. So the basis is the following, that s is empty, right? Then what do we obtain for this? So the app of empty and empty, and this is equal to what? To empty string, right? By definition, yes? By definition, this is equal to this. So it holds. So for s empty string, this is true. Next, what do we need to do next? So let's suppose that, so let's take s equal to what? So this is the induction step. So which one? Yeah, how can I write that? So if some string is not empty, then we can write this, that this string is equal to some string, so some s prime and x here, okay, x column s prime. And now we have to prove this for this one, right? Induction step, or how do we write that? Well, hypothesis, this is the induction hypothesis. Yes.
We usually assume that this is true and then.
Okay, yeah. Well, but so we are assuming that this is true. So this is the induction hypothesis, okay? But now we are taking like two steps. The first step is the basis, and then the second step is when we take s for any string, okay? So I think it's step, yes, okay? Okay, so what do I need to do then? Yeah, just write this here. S. This is equal to what? X column up of S prime. And this is equal to what? Yeah, then we use this. So we use this for S prime, and then this is true. Then we obtain that right? Yeah, S prime. And this is equal to S. That's it.
Why is prime?
Because this is empty set. So because look, this is
I was going to show that F and S and empty will be empty.
yeah. Wait.
But how can we get
Yeah. Wait. Yeah, this is. Where's the problem here?
according to our
This should be empty. Yes. Empty.
and that is
And that is
X.
X. Y is. Yeah, that's not good. Where's the problem here? So we assume that this is true for.
So the property is not true.
No, it is true. We have some mistake here. But I don't see which one. So did we take the what are we going to try to prove? This one, yes. So empty set. Let me check. I don't see the problem here. Ты видишь, какой проблем? Так. There's something wrong, but what did I do wrong? Any ideas? Okay, so yeah, this is true. And then we obtain that, yes. This is S here. What are we saying? This is S, of course. This is not empty, but this is, yes. Not empty, but S. That is what we want to prove, of course. Yes, we want to prove this because we want to put that that this is, yes, that this has to be T here. And since this is empty, then T should be empty string. Yeah. Okay, so we were proving the wrong statement. So this should be equal to this because, so we have this.
I think we have to prove that F
Yeah, that's what we are doing. Look,
Not
we have that for definition. For definition, what do we know? We know that app of s, no, of empty string s is equal to s.
so we don't know to prove it. We don't need to prove anything in that case.
We need to. No, wait.
We don't need to.
No, by definition we have then this s here, and yes. Okay, I'm confused. So by definition we have this. Do we have this by definition? I already do you have that? Yes. We have this by definition. And then we obtain this. And this should be equal to this is equal to empty, so yeah.
So we needed to.
Yeah, so we didn't need to prove yes. The order was correct. Okay. Anyway, let's finish the proof because. So.
Science here there is a mistake here. F of s and mt is equal to s. We already suppose that s is equal to mt. Why need to use this in a equation?
Here?
Science here. Something we don't need to prove.
No, this is just in general, in the general case. I thought we had to prove it because I thought that by the definition it was this way, but it was correct. So we don't need to prove it because, so here it should be written t. So t is equal to, so t is an empty string, right? But I wanted to prove that if we have here s and empty string, then we obtain s,
So
okay?
this is another part, not part of the exercise.
Yeah. But let's finish the proof already. So this is this is and then this is s. And now the proof is finished, okay? Okay. So yeah, we didn't need to prove that, but we already did it. So this is the case 1. And now the case 2. So S is not an empty string, yes. Then what do we obtain here? We have to put then this here, app of this, and this is equal to x app right? And this should be equal to what? To empty set, to empty string. What can we see here? So we are saying that empty string is equal to this. This is what? So what are you saying? Yes? So is this possible or not? Why? Yeah, this is empty string and this is some x column some string. Is this possible or not? This is not possible. Why?
Because we have already have an element.
No. Don't talk about element. We don't have sets here. We don't know what a set is. We have strings. Okay? So you cannot say this is not true because we have some element here. No, this is not a set. Yeah, this is a set, but we don't know that.
Here we should take we took x s
Yes.
And then we have to prove that this is true.
And then we say, and then we take this, so this from here, we put S here, and we should say that this is equal to an empty string. But this is equal to this. And this is not possible because of the definition of an empty string. So an empty string cannot be some x column S prime. This is not possible by definition. So we got a contradiction here. Okay?
It means that the property signs like 45, 40, 40, we have to prove that, right?
40? What 40?
Like in the exercise, we have to prove that f of S and T equal to MP is equivalent. We have to
Yeah, if and only if this holds. And we already saw that if this is empty, then T is empty. But if S is not empty, so we got a contradiction. So this cannot be empty. And that's it. Okay? So in this case, it's very important that, yes, this is not true, but I'm going to ask you why. And you have to tell me the correct answer, that not because we don't have some, because we have some element, or because this is obvious or something like that. You have to tell me because of, by definition, the empty string cannot be equal to this, to x column S prime, okay? And this is the correct answer. Okay, that was number, yeah, we prove it. Why not? So we take two values. How many values how many strings can we take for S? Empty or non-empty, right? We take empty, and we obtain that this is empty, then end T is going to be empty. And we take a non-empty, and we got a contradiction. So S only can be empty, and since S is empty, then T is going to be empty string. Okay? That way. Okay, next. How many times? Oh, well, almost finished. 15. I don't know if we have time for 15, but let's try.
T must be empty.
If S is not empty, then we don't know anything about, so this is not possible. It's not possible that S is not empty.
We took first S is empty and prove that T is empty.
Yes.
And the second one, we have to take S is equal to some string,
Mm-hmm.
and then T must be what?
This is not possible. We just said S is not empty. But if S is not empty and we put it here, then we get a contradiction. Then S cannot be empty at all. Okay? So it's T doesn't matter. If T is just, we just say T is not, S is not empty. So I think that's it for today, because we have a long exercise. So thank you very much. So I understand that only 2 persons send me your exercises, right? So I remember you. If you want to discuss your solutions, you have to send me your solutions in PDF. Okay. The deadline is every Tuesday at 2 p.m. Okay. So just before we begin our seminar, and that's it.
When is the final deadline for the first assignment? Is there any deadline for the whole first?
Could you please ask that to the lecturer, because I also ask, and so I don't know.
Can I explain? Can I say part by part? For example, this week I can maybe explain one part.
Yeah, you can explain whatever you want. Yeah, one exercise of all, it doesn't matter.
Grade me on that section alone. Or,
What?
for example, if I do section number 1 and then you will grade for whole section.
Yeah, you can do that. You can, whatever exercise you want all, you want just two, it doesn't matter, okay? Thank you.